The next section we're going to look at is section 2.5, which is solutions via substitution. So far, we know how to solve several different types of ordinary differential equations. We talked about those that are separable, where you can get like the dy and the dx terms on opposite sides. So you can make it look like dy with some, I don't want to use f, but let's say, some function of y is equal to h of x times dx, and then we can solve those via integrating both sides. We also talked about how to solve linear first order DEs. We have our dy dx plus p of x y equals f of x. We know that for these we can use an integrating factor that is e to the integral of p of x dx to turn it into a exact differential and then integrate to solve. And then in the last section we looked at exact differential equations whenever the partial, so if it's written as m dx plus n dy is equal to 0, if we have m of y is equal to n of x, then we have exactness, and we can solve it by integrating some partial derivatives and then differentiating to find the constant of integration function. Furthermore, we also saw some examples that weren't exact, but they potentially could be turned into exact differential equations if they met a certain set of conditions. So that's already a fairly nice class of ODEs that we know how to solve, but certainly there's a lot of bigger fish in the pond. And in particular, what about some other types? What else is out there for us to look at? So there's a lot of different types of differential equations, more so than we'll ever be able to cover in a single course. But we're going to look at some now that don't fit into any one of those categories we've already seen previously, but that oftentimes can be resorted to and transformed into one of our basic types via some type of solution. And so what we're going to look at in section 2.5 is solutions by substitution. In particular, the three kind of types that we're going to look at are going to be homogeneous differential equations. We'll look at a Bernoulli differential equation, and then we'll look at one that can be turned into a separable. Okay. The basic idea here is, let's suppose we have our classical differential equation. So we have dy dx is equal to some function of x and y. And we look at it and we say, okay, it doesn't fit into any of the types of models that we know how to do already. So what we might try to do is, let's try to make a substitution here. Okay. So let's suppose that y is equal to, so we always think of y as being some function of x, but let's suppose that y is equal to some function g of x as well as a variable u. Okay. We can calculate dy dx using the chain rule in three variables. Dy dx would be the partial derivative of g with respect to x times the derivative of x with respect to x plus the partial derivative of g with respect to the second variable u times du dx. For the partial notation, let me just kind of use the old school. I'll just call this, it's going to be g sub x, the partial of g with respect to x, dx over dx is just 1, plus this will be the partial of g with respect to u times du dx. And furthermore, where we see dy dx, recall dy dx was equal to f of x comma y, which now we're presupposing is equal to f of x comma, what's y? Well, y is g of x comma u. Okay, so this is f of x of g of x and u, and the u itself, we're thinking of u also as being some function of x. So we're still thinking of y as a function of x, but of a particular form. Okay, so we have y is dy dx equal to f of x comma u. And so if I plug this in down here, this is what we get. F of x comma g of x comma u is equal to g of x plus gu du dx. Okay. We can solve this. Let's solve this equation for du dx. Okay. Du dx is going to be equal to, so I have f of x, g of x, u, minus gx divided by gu, which simply put, I want to think of as some function of x and u. Okay, so here's what we have. We have du dx is some function of x and u, and the idea is that maybe this differential equation is something that we can actually solve, and is one of our known types, whereas this original differential equation perhaps was not. And let's suppose we can actually solve this. Let's suppose we solve this for u. Remember, u is a function of x. And let's suppose that it has the form psi of x. So if we're actually able to solve this, then that gives us the solution to our original ODE. So then the solution to the original ODE, remember, it was y equals g of x comma u, which is going to be y equals g of x comma psi of x. Okay, and so this is going to be the basis for how our substitutions are going to work. We're going to try to do this kind of substitution, and we'll look at it in a couple of different specific scenarios where the substitution actually will work. It will present us with a differential equation that we can solve in terms of the variable u, and then that'll give us a solution to our original starting ODE.